So to give you a little bit of background about myself, I've been doing research in atmospheric dispersion for some time. I've also been doing research in combustion. And so this is one of those unique opportunities where both these problems come together. And so this is my perspective where I'm coming from. So what I'd like to do is talk about how you understand the hazards and consequences that we have here. First off, I want to talk about the typical transportation and storage conditions. My focus is going to be on transportation and storage as opposed to normal operations. If you deal with transportation and storage, then those operations are normally outside, outdoors, okay? And so the distinction there between the process conditions, they may be confined, associated with either the presence of vessels nearby or controlled and confined spaces. And so the issues that you get into then as a consequence are much different. I'm going to focus on the transportation and storage. I'll talk about the potential for the loss of primary containment, LOPC. The two issues that we've talked about these already, are fire and explosion hazards and then also toxicity hazards. I'll talk about some LOPC scenarios, ones that I've looked at. I don't think that they are exhaustive because it's quite clear that others have looked at these scenarios in a very detailed fashion. I'm going to focus on three only to try and get down to the essence of those. And then I'll talk about how to do the modeling of those identified scenarios and hazards. And then lastly, some mitigating effects, and then hopefully draw some conclusions. So as far as the transport and storage conditions are concerned, typically you're talking about three types of cases. The first is a refrigerated case where the temperature is below the normal boiling point and at atmospheric pressure. Semi-refrigerated cases where you've got a temperature above the boiling point and also then the pressure is above 1 atmosphere. And then finally pressurized cases where you've got the temperature at the ambient temperature and then the pressure is greater than the vapor pressure at the ambient temperature. So those are the three that I'm looking at: refrigerated, semi-refrigerated, and pressurized. So as far as the hazards are concerned, the first one of those has to deal with the fire and explosion hazards. Now, I've listed the normal hazards associated with fire to start with. Of course, if you can have fires. You can have fires associated with ammonia. Those typically are associated with operating conditions, okay? They're not normally associated with outdoor storage or transportation conditions. But nonetheless, those sorts of events do occur. Once you go past the normal consequences of fire, then there are two things that you get into. One of those is deflagration. That word's been mentioned here earlier today as well. And then also the detonation. Now, the thing about a deflagration is that it can be referred to as a flash fire. It's got a lower maximum side-on overpressure, okay? The thing that people overlook frequently when they're talking about explosive impacts is that all surfaces around us have atmospheric pressure pushing on them, okay? The thing associated with an explosion is that an explosion gives you a pressure above ambient pressure, but it does it for a brief period of time, okay? For a deflagration, those time periods are on the order of tens of milliseconds, okay? Very short period of time. And normally overpressures, even if you look at tables of overpressure damage as a function of the type of damage, then tables will list things like destruction of houses as 1 psi. Well, that's 1 psi above ambient pressure, so that's an increase of about 7%, okay? It occurs over a brief period of time, a few milliseconds, but the point is it can still have devastating effect. And so the devastating effect is there as a consequence of those two things, the increase in pressure, that short duration, okay? And so and the reason is because most materials are not made to take that sort of impact. They simply they simply can't move at that rate of speed, okay? And so that's where the damage comes in. If I do that to a fluid, then the thing is that the pressure wave will pass through the fluid without any change associated with it. And that's the big distinction between solids and fluids. And that's going to be important even to answer Professor Grader's question earlier associated with the impact of an explosion on a refrigerated vessel. Because the refrigerated vessel is a fluid, okay? There's very little increase in internal energy associated with the fluid under those conditions. There is dramatic difference associated with structures, though. The structures are deformed permanently, okay? And so that's the difference between a fluid and a structure. So I've got deflagrations, then I've got detonations. Those are much higher maximum overpressures, those occur on very short time scales, a few milliseconds as opposed to, a few milliseconds or microseconds as opposed to a few milliseconds. I'll get it right eventually. And so the deal here is that those are associated with energetic materials like TNT, for example. Those are the sorts of materials that react very, very rapidly. They generate this high pressure over a very brief period of time. They have damaging effects. And so that's what we've got to deal with. Normally, if you're talking about consequence assessment, like a chemical cloud, even a cloud such as like the Flixborough accident was mentioned earlier, where cyclohexane was released and then it hit an ignition source after the vapor cloud had formed, that was a deflagration. The characteristics of the deflagration are this much lower maximum overpressure over a much longer period of time. And so that was the devastating effect there. The detonations are really materials that are highly energetic, such as TNT. Deflagrations can be accelerated to detonations. Those things occur for hydrocarbon fuels typically when you're talking about congestion. So if I've got, for example, there are many examples of accidents where parked cars even with a vapor cloud amongst them has resulted in detonation velocities because of that congestion, even though the event started as a deflagration. So it accelerates because of the turbulence when you get flow around objects. Turbulence creates mixing. Mixing, it's basic chemistry. Turbulence creates mixing. Mixing enhances the reaction rate. When the reaction rate increases, the amount of energy that's produced increases. It increases over a shorter period of time, and you get this buildup effect that causes the devastating effects. Okay, so really and truly, that's kind of one of the themes here, is that the appropriate thing to think about in all of this is going back to some of the basic chemistry ideas and their appropriate application. And then the last thing I want to talk about, of course, is going to be the toxicity hazards, and those are frequently characterized with these eagles. You all have heard discussions about that before. But so let me talk about the fire and explosion first. So the thing that's important here is that the consequences of fire explosion depend importantly on the total amount of energy that's released, but also how quickly that energy can be released. And so the total amount of energy is going to be proportional to the heat of combustion. And so I've got just some examples here. I've got ammonia, I've got ethanol, and I've got hexane as a stand-in for gasoline. So as you can see on this, the reason why gasoline is used as a fuel is because it's got a pretty good energy density, right? You've got a large amount of energy per unit mass of the fuel in comparison to ethanol, which is why when you do that, you typically blend ethanol with gasoline because of the disadvantages that you'd have with a pure ethanol fuel, liquid fuel in a motor vehicle, for example. And then you also see there that ammonia does not have nearly as much as the other materials, okay? And so these are all just very basic heat of combustion calculations. And so if I were looking at this, I might suspect that the gasoline would be if I were just looking at the heat of combustion, that the gasoline would be the most important fuel here as far as what might be the consequence of a fire, a potential fire, or deflagration or detonation, right? And so I've got, so what I wanted to do was I wanted to show you an ammonia fire video. There is one that's available on YouTube. You can look at it. It is interesting. I think that one of the things, a couple of things that are important about it is to recognize that it's a pre-mixed volume, okay? So you've mixed in this particular video, you've mixed in the proper amount of ammonia and the proper amount of air so that you're within the flammability range associated with the ammonia. So all of the material's pre-mixed, okay? That's important to remember and keep that in mind because that's going to be an important fact that we'll have later as well. And then as you can view in the video, as the fire starts, then I see some of you all are pulling out your phones to look at the video now. That's great. So anyway, as the fire starts, then you get this fire that's actually pushed out of the Connex container, and it seems like, gosh, this could be a problem. But the thing is, let's compare it to some of the others. So if we look at gasoline, and the reason why I have these videos is one of the things that I do is I teach a chemical process safety class, and so I try to make sure that the students understand the importance of the numbers and what the numbers actually mean, because even though fire everyone in this room has some sort of experience with fire, okay? But the problem with that is that as a consequence of it, you may think that you understand fire quite well because of your familiarity with it. However, that's typically not the case for human beings. They tend to think that they understand things when they're familiar, and that's not always true. I read an article recently that essentially said if you talk to several people and ask them how a flush toilet works, they won't be able to explain it. And so that's the sort of situation that the gap that we get into with understanding. So let me show you this video. Okay, so first off, this is gasoline, so obviously I'm going to light the gasoline. Everybody's seen a gasoline fire in the movies, and you expect this to blow up, right? Okay. Anybody not expect this to blow up if I light this? Okay, so the point is that if I'm basing this only on heat of combustion, then this should be pretty devastating, right? But it turns out it's not. And so let's do this. The other point that I use in this class to illustrate is how you can actually, now remember that you've got the basic fire triangle, you've got to have an ignition source, so I'm going to provide the ignition source. I've got gasoline, and now I have a fire, okay? Large heat of combustion, but the problem is that the fuel inside the container is outside its range of flammability. And so I'm able to put the fire out with a simple screen, just a bug screen that just, all it does is it dissipates heat. Still allows the air to go through, still allows the heat to be there. But what it does is it dissipates the energy of the reaction so that the reaction is no longer self-propagating, okay? So it's not just the heat of combustion. It's not even just the mass of material. It's also, importantly here, the amount of air that's mixed in. And so that's kind of the thing to take forward on that. So now I've got an ethanol fire video. This one's a little more entertaining. And so it's in a standard container at room temperature. And I used to do these demonstrations to the class with a can so that I could shake the can and you could hear that I only had a very small amount of liquid in it in both cases because I was using one of the principles of inherently safer design, that the minimum amount of material minimize the consequences. And if you're doing it in a room like this, the university always frowned at me when I set fire inside a classroom. So I had that issue, okay? I ended up having to quit doing this in live demonstrations because the class size was just too big. But anyway, so I made videos of all these, and so here's and so hopefully we've got the sound on this video at this point. So let's see if it'll go. I shake up the can before I put it down. Oh, we don't have any sound. Okay. You would hear a nice little growl if we had the sound on this. Hint, hint. But this is in slow motion. This is a 1 gallon can. The previous was a 1 gallon can as well. You can see that I get a nice jet fire out of this. And so this works quite nicely. Ethanol has a lower heat of combustion, but because of it's within the flammable limits, the amount of air that's mixed is important. It actually presents a greater hazard because it releases more energy over a shorter period of time, okay? And so that's the important thing to take away from all this. So I've got those, let's see. So I've got the fire videos, and so I think I said just what's on there. It depends on the total amount, but also the amount of air in order to actually do this. And so the question is, well, how much air is needed? And so I've got now the lower flammable limit and the upper flammable limit presented there. And so once again, for comparison, of course, the LFL is when I've got just sufficient fuel. The UFL is when I've got just sufficient oxygen. And so I have to have both those things in order to meet this. And so I've listed the LFL and the UFL for ammonia, ethanol, and hexane again as my stand-in for gasoline. And you may have heard people say that ammonia burns in a narrow range. Well, I look at those numbers and I think, well, that's ridiculous. That's not the case. I mean, 28% to 15%, that's a 13% range. How different is it than the gasoline, the 3.3 to 19%? It's not when I just look at those numbers, okay? The point is, now though, if I think about this for a second, really what I'm talking about is the amount of air that I've got to add to this in order to put it in the flammable range. Okay, and so I calculated these columns. For the LFL, for the LFL, I calculated the volume ratio of air that I would have to add per fuel in order to do it, and I calculated the volume ratio at the UFL of the air that I would have to add per volume of fuel. And so for ammonia, those numbers are 5.7 volumes and 2.6 volumes. Okay? And so the deal here is, the reason why this is said that that's a pretty narrow range is because the ratio of those two is only a factor of 2 for ammonia. So really, you have to be within a pretty narrow range associated with ammonia. You don't see it when you look at the percentage of fuel in the mixture. You do see it when you see the amount of air you have to add. Okay? It's quite clear. It's much narrower than either ethanol or hexane. And the other thing to notice is that the fuels are about the same. The ethanol and the hexane are about the same as far as those numbers are concerned, and that's pretty typical. Okay? If I'm talking about hydrocarbon fuels, those numbers are not very different across all fuels. Okay? But for ammonia, it's greatly different, and furthermore, it's narrow in comparison to everything else. Okay? Now, if you've read ahead though, then I've spoiled the surprise because I didn't have my points hidden. And the point is on the bullet down there it says if I've got an instantaneous release of a pressurized ammonia storage, if I have an instantaneous release, the experience from accidents in the past for ammonia has been that roughly 10 times the amount of air is mixed in under those conditions per amount of ammonia. And so the point is an instantaneous release of pressurized ammonia is going to give me a ratio of air to fuel of 10. And that is greater than either of the ones associated with the LFL and the UFL. So the point is, if I've got an instantaneous release of pressurized ammonia, it's going to be outside the flammable range as soon as the release is over. That's important to know, okay? Because now that says just the consequence of the release itself. If I'm out in the open, now if I'm in confined space in a plant, different matter, totally different matter. But if I'm out in the open, now I see that that amount of air is going to be mixed in. I'm going to be outside the flammable range. I'm not going to have any issues, should not have any issues associated with fire under these circumstances. Okay? Okay. Let's see. So then I've got some conclusions. The impact of a fire is strongly dependent on how quickly the energy is released, and this depends on the amount of air that's present. There's a limited range of the amount of air added to an ammonia cloud necessary for it to burn. And furthermore, if I've got an instantaneous release under pressurized liquid conditions, then I'm going to be mixing more air in associated with the release that will actually push me out of the flammable range. Okay? And so my cloud will no longer be flammable. So now then, well, what about explosions? Detonations have actually been observed in experiments using ammonia-oxygen mixtures. Okay? I actually found some data that showed that. I was really kind of surprised. But I did find some data that showed those experimental velocities. Now, these were experiments. This is a situation in a laboratory where you've got a mixture that's homogeneous and it's within the flammable range. So the point is, if you have a mixture that's homogeneous in the flammable range, you can produce a detonation with it. Okay? The issue is how much material you would have in that flammable range and whether you can support it or not. And so, though to do this, I've got to have an explosion. I would have to mix in the proper amount of air, and the experiment, to emphasize again, the experimental data was ammonia oxygen, not ammonia air. That's important to know also. And I would have to mix in the proper amount of air within this narrow range and have a large amount of that in order to produce an explosion. And so in an accident scenario, even under a situation where I might have some sort of malevolent act, that's going to be, well, essentially no risk associated with it. It would not be a practical scenario for an accident. Okay, so let's turn to the EGLES, the AEGLs. So the EGLES, by definition, you all may have seen this before. The important bit is that it includes susceptible individuals. That's the first thing. And then the second thing is that the wording is could experience these effects. And so we've talked about EGLES 1, 2, and 3. Those are the definitions. EGLE 3 is the one I'm going to focus on because it ends up being the one that most people are ultimately very interested in. EGLE 2s are important as well. But just for the sake of argument, I'm going to focus on EGLE 3, which, of course, are the life-threatening health effects or death. Okay? And so this once again is the level where these things could occur. Okay? So typically these are based on a minimum probability. And when I was preparing for this, one of the things that I did was I went to the EPA website and they actually have the background document that's available for the development of EGLES. I read through the document, and In the case of ammonia for Eagle 3, it was developed on the basis of a Probit equation. And so, that's what's in the documentation that's there. It turns out that the value is, and it's based on the LC of 1%. And so that is out there as far as the documentation is concerned. The Eagle 3, when you plug in the numbers, they actually have, it's based on C squared times time, the concentration squared times time, where the concentration's in parts per million and the time's in minutes. And so you can get some value then that they will have out there for Eagle, they have different times for the Eagle 3. And so if you look at those and you can take the chart and do C squared times time, and you'll come up with the same value for all those numbers. What that means is that because it's a Probit function, and that's a causative variable, that means that really all I've got to do now is worry about the integral of C squared dt. And so if I've got concentration time histories, that gives me the causative variable as long as my causative variable adds up to this number of 7.3 times 10 to the 7th. I got to do it in the proper units. But as long as I do that, then that will tell me what the Eagle 3 exposure is. And so I can use that quite effectively. So now I focus on the LOPC scenarios. For the LOPCs, then I focused on three things: the refrigerated liquid ammonia released onto water. What I was assuming there was that there might be some sort of loss of containment on a ship when it was in the water. Okay? And so you assume that you have a refrigerated liquid release on water. And so this has been discussed before, that on small scale tests, these were the ADL report for the Coast Guard. On small scale tests, they said 70%. I think that this was probably a saturation situation. When they did larger size, they were still spilling on the same pond, and so they were probably saturating more of the water around. And so they got a lower value. If you're in the Mediterranean, then I would expect you to get, at least the 50%, maybe more, because you're going to have water circulation and things like that. And so what I concluded from that was, and what they observed was, that it looks like this would be appropriate to be modeled as a buoyant plume. Now, there's been some question about whether this is buoyant or not, and so I'll go ahead and address that at this point in time. One of the things, and I'll show you in a minute, that we did was we actually looked at modeling the Desert Tortoise releases. Those were a series of pressurized ammonia releases. And so one of the issues that you get into is questioning what happens associated with the water droplets. And so there have been studies. There was a study that was done by Chris Wheatley at the Safety and Reliability Directorate, the same people that had the previously mentioned report by Jeff Kaiser that indicated that there might be some sort of interaction associated with ammonia and water. Chris did a great job of going through and actually looking at a thermodynamic model that would take into account those interactions. You look at the heat of, you can include in the model the heat of vaporization, or the heat of mixing associated with the ammonia water. You got to recognize in that process that the process of taking ammonia into water, which is what could be done, and it works thermodynamically either way, that's really a chemical equilibrium. And so once again, you're in a situation where you've got vapor-liquid equilibrium going on. And so when you take all those things into account and you recognize that the reaction is an equilibrium reaction, then the droplets will simply evaporate. And so there's no additional formation of any other ammonia species that's a solid. It just doesn't occur. And so those things are there. The semi-refrigerated liquid vapor ammonia release over water, underwater, what they found in the ADL report was that as long as you were, about about 9/10 of a meter, as long as you had that depth, you didn't see any vapor over water coming out. And then the last one was the pressurized releases on land. And so that one, I assumed essentially an instantaneous loss of primary containment. And so, and if I do that, then I can model that as an air ammonia cloud, as I indicated before. I'm going to mix in a specific volume associated with that, and so I can go from there. In this case, I'm going to be only looking at toxic consequences because the flammability is already gone. I'm below the flammable limit when I treat the release in that way. So I used the Degatis model. That's the model that we developed for the Coast Guard. It was used by the EPA also. It was developed for for denser than air gases with low velocity sources. And so this was something's been mentioned of an area source. And so the original ground level model used an area source and then predicted the downwind dispersion, taking into account the density stratification and the reduction in mixing that you have from the atmosphere from a Gaussian plume model. And so that's there. And then the other model that we developed in conjunction with this was for the EPA. And so this is actually, it was meant to model emergency relief valve discharges that were vertically up in the air. And so once again, you can have a situation where the material indeed was denser than air and then would come back down. And so this is a little cartoon then of the plume that rises up. If it's denser than air, then it will come back to ground level and you'll get an area source then and disperse downwind. And so that's the way the modeling works as far as those things are laid out. So it takes into account the buoyancy associated with the release and that sort of thing. And so like I said, we compared that with desert tortoise. And so here's a bunch of numbers. If you look at the numbers, this is all fairly reasonable. In the way this works, the dark gray line is the observed value. The light line is the Degatis predicted value. I did not change the model as a consequence of the comparison with these tests. This was developed on previous data. And so you can see that in general there's, within a factor of 2 normally associated with these. The thing that's important about denser than air releases, and you see it in the sigma Y and sigma Z, is the denser than air gases are characteristic low, close to the ground, and very wide. And so that's reflected in the observations and the predicted values. And the other thing to point out is that the predicted values are within about a factor of 2 of what you have even downwind when you've got the transition into essentially passive behavior. Okay, so that's that. And so then I wanted to look at some example scenarios. Now I want to be very clear up front that these are associated with purely examples. I did not have specific information that would be pertinent here. These are meant to be simply show you some possibilities associated with potential consequences. Okay, so I looked at this. This is the refrigerated liquid on water release. This is actually a picture of those Author D. Little tests. They released the ammonia on the water there, and as you can see, the puff that was formed as a consequence of that goes straight up in the air. This was under low speed conditions, and so that's why it goes straight up. If you have higher speed conditions, then it will be blown to the side, of course. And so just as an example, I used 100 kilograms per second. That's the same release rate as the desert tortoise. That ends up being about, I think it was 3 times larger than the largest rate that has been used by previous speakers. So this is maybe large, but this is what I used associated with the rate, assuming you've got a loss of containment from a ship. Based on the DOT experiments, about 50 kilograms per second is going to go downwind, and so I assumed that was the case. And so I ran a couple of scenarios, meteorological scenarios, 2 meter per second winds, F stability. I happened to look on the HIFA weather website on the day that I was preparing these, and it looked like that was probably a pretty reasonable range associated with this. Was 2 meters per second. I don't know whether it was F stability or not, but that would be typically the worst atmospheric stability case. And then 10 meters per second D stability, that was roughly the maximum wind speed that was that day. And so downwind distances to Eagle 3, 2 kilometers to 1 kilometer, with elevations, though, that are 240 meters and 70 meters. Notice that the high wind speed case is actually lower, and the reason for that is because the wind pushes it toward the ground more. It bends the plume over more quickly. The other thing that's kind of interesting is that the lowest elevation, where I had Eagle 3, was always near the source. And so the deal here is that as long as the elevation is not going to be a trouble, which it might be with Mount Carmel. I don't know what the elevation of Mount Carmel is, but nonetheless, those seem to be the maximum numbers, at least the way this was modeled. Okay. If you all have questions, please let me know what we're talking about. So then the next scenario then I looked at after discounting the release underwater was the pressurized liquid release on land. And so in this case, I assumed I had 12.5 metric tons instantaneous release that gives you an adiabatic flash fraction of about 18.8%. I assumed I mixed in 10 times the volume of air, and then I discounted any reaction between ammonia and environmental surfaces. Ammonia is known to react with environmental surfaces, and so I did not include that effect at all. And so once again, 2 cases, 2 meter per second, 10 meter per second winds. And so the distances then ended up being on the order of about 1 kilometer for that c squared dt, the integral of c squared dt term for those. Okay? So then the other thing that obviously is a question is what happens if you have an external energy source. And so those could be explosives or mortars. And so the idea that I took was that you could increase the energy then associated with the material. And so then what magnitude of impact might it have? So I recognize that not all the energy of an explosive would go into the material itself, but for the time being, let's make that assumption. And so I assumed 100% efficiency. And I just looked for the example purpose. I did have some information associated with mortar rounds that have been tested in the United States. And so some of the rounds that I saw were on the order of things like a pound of TNT, 450 grams of TNT. And so if you look at that, 450 grams of TNT is enough to vaporize 1.5 kilograms of ammonia. Now this gets back to Kent's point earlier today that ammonia has a relatively high heat of vaporization. So the point is that even if I take all of the energy from something this size, it's only going to vaporize this. If I'm talking about a release of 12.5 tons, it seems the impact will be insignificant. And furthermore, if I think about scaling this to larger amounts of explosive, then I think that the issue may become the explosive and not the ammonia. Now, it's entirely possible, though, that the explosive could breach more than one tank. I did not consider that at all. But obviously, if you spread energy over that, then the impact of any such potential event could be the simultaneous loss of containment with the vessels as opposed to the actual energy that's released associated with the explosives. So that seems to me the primary concern here is figuring out what's the vulnerability associated with the number of containers that could be breached simultaneously. So then reaction with environmental surfaces, this is typically done with dry deposition. Dry deposition velocities have been reported for ammonia, and they are considered a significant amount of a chemical reaction with environmental surfaces. All of this work has been done at low concentrations. If you think about it, the flow over water is going to be much more impact, or it will reduce the ammonia concentration much more than flow over land. And so as long as, if that's the case, then that will be to the benefit. So my conclusions, impact of a fire depends upon the amount of energy and the amount of air you've got. I've got a limited range really for ammonia when I look at the flammability range. If I've got an instantaneous rupture of pressurized ammonia vessel, then I don't believe the cloud will be flammable because of the amount of air that's mixed. If I'll have to be in those ranges in order to that. We've seen detonation in experiments, but those experiments were for pre-mixed materials. I've got a way to look at the probit-based causative variable for Eagle 3, and then I looked at the 3 basic modes of primary containment. I'm running out of time, so I'll just skip over that. And these are the things that I've said before. The only thing that I haven't said before, I believe, is the last point. And the last point is that if I'm talking about a denser than air gas, one of the things that is different from this in a passive gas is that the worst case meteorological conditions may not be the low speed F stability. You've got to look at a wider range of those. And so I think that I've said everything that I hope to say. So thank you all very much.